Welcome to IQriously. Get comfortable. Take a slow breath. Look up. Or imagine looking up. On a clear night, away from the glow of cities, the sky above you is crowded with light. Thousands of points of light scattered across the darkness in every direction, some bright and steady, some faint and trembling at the edge of vision. Each one of those points of light is a sun, a star, burning, enormous, unimaginably far away. And every single one of them has a story, a beginning, a middle, and an end. Tonight, we are going to trace that story. From the cold, dark clouds where stars are born, to the quiet embers of their endings, and to the extraordinary fact that you are made of what they left behind. There's nothing you need to do. Nowhere you need to be. Just listen. Before we begin the story of stars, we need to spend a moment with the numbers. Because the universe operates on scales so large that the words we have for them do not really do their job. When we say a star is far away, we are using the same word we use for the distance to the next town. But the distances involved are of a different order entirely. The nearest star to our own sun, a small, dim star called Proxima Centauri, is approximately 4.2 light-years away. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In a year, it covers roughly 9.5 trillion kilometers. Proxima Centauri is 4.2 times that distance away, about 40 trillion kilometers. If you drove there in a car at motorway speed, without stopping, the journey would take approximately 50 million years. And Proxima Centauri is our nearest neighbor. Our galaxy, the Milky Way, is approximately 100,000 light-years across. It contains somewhere between 100 and 400 billion stars. Some estimates put the number higher, 100 to 400 billion stars. In one galaxy, the observable universe contains somewhere between 1 and 2 trillion galaxies. These numbers are not really numbers in the way we normally experience numbers. They are gestures towards a scale of existence that the human mind was not built to fully grasp. And yet this is the context in which our story takes place. A universe of incomprehensible vastness, filled with stars beyond counting, each one burning through its own life cycle over timescales that dwarf the entire history of life on Earth. Let's begin at the beginning. Every star begins its life in darkness. Scattered across the galaxy are vast clouds of gas and dust, molecular clouds, the astronomers call them. They are enormous, cold, and almost impossibly thin. The densest parts of these clouds are still far more empty than the best vacuum we can create in a laboratory. They are composed mostly of hydrogen and helium, with traces of other elements. And they are beautiful. The most spectacular images from telescopes like Hubble and James Webb, those great glowing structures, the pillars and curtains and towers of rose-colored light, are photographs of these molecular clouds. Stellar nurseries where stars are being born. For millions of years, a molecular cloud drifts through space, enormous and quiet and essentially unchanging. But eventually, something disturbs it. Perhaps a shockwave from a nearby supernova, the death explosion of another star. Perhaps a gravitational interaction with another cloud or a passing galaxy. Something ripples through the gas, and in certain regions, the cloud begins to collapse. Gravity takes over. Where the gas is slightly denser than average, it pulls in more gas. The denser it becomes, the more powerfully gravity pulls. A clump forms, then a core. The material spirals inward, growing hotter and hotter as it compresses. This early object, not yet a star, but something on the way to becoming one, is called a protostar. it is surrounded by a rotating disk of gas and dust. Material continues to fall into it from this disk. It grows. It heats. For thousands of years, for hundreds of thousands of years, it collapses inward. All the while, it is getting hotter. And then, at a temperature of around 10 million degrees Celsius, at its core, something happens that changes everything. Nuclear fusion ignites. Nuclear fusion is the process that powers every star in the universe. It is the joining together of atomic nuclei. Hydrogen nuclei, the simplest atoms in existence, a single proton each, are pressed together under conditions of extreme temperature and pressure until they fuse into helium nuclei. And in the process, a tiny amount of mass is converted into an enormous amount of energy. Einstein's famous equation describes this conversion. E equals mc squared. Energy equals mass times the speed of light squared. The speed of light squared is an enormous number. Even a tiny amount of mass, converted into energy through this equation, releases a staggering amount of power. In our own sun, approximately 600 million tons of hydrogen are converted into helium every second. Every second. And in the process, about 4 million tons of that mass are converted directly into energy. 4 million tons of matter, every second, becoming the light and heat that falls on your face when you stand in the sunshine. The moment fusion ignites in a protostar's core, two competing forces reach a balance that defines a star's entire life. Gravity pulls inward. It always has, and it always will. Left unchecked, it would compress the star into ever greater density, eventually crushing it out of existence. But fusion pushes outward. The energy released by fusing hydrogen creates pressure, radiation pressure, and thermal pressure that pushes the outer layers of the star away from the core, outward against the inward pull of gravity. When these two forces balance gravity pulling in, fusion pushing out the star settles into what astronomers call the main sequence. A stable, sustained equilibrium. A long, burning, steady adulthood. This is where our sun has been for the last 4.5 billion years, and where it will remain for roughly another 5 billion. The main sequence is the longest phase in a star's life. For most stars, it lasts billions of years. For our sun, the total main sequence lifetime is about 10 billion years. 10 billion years of steady fusion, of hydrogen being converted to helium day after day, in a process so reliable and so consistent that a planet orbiting at the right distance can develop oceans and continents and eventually life. But not all stars live the same way. And here is one of the great paradoxes of stellar evolution. Bigger stars burn faster, much faster. A star 10 times the mass of our sun is not 10 times as luminous. It is thousands of times as luminous. It burns through its fuel at an extraordinary rate, living brilliantly but briefly. A massive star might live for only a few million years, burning so hot and so bright that it blazes blue-white in the sky, spectacular and short-lived. Meanwhile, the smallest stars, the dim red dwarfs, no more than 1/10 the mass of the sun, burn so slowly and so efficiently that they can remain on the main sequence for trillions of years. Longer than the current age of the universe, which is only about 14 billion years old. A red dwarf star that formed in the first billion years after the Big Bang is still on the main sequence right now. It has barely begun its life. It will be burning long after every other type of star that currently exists has ended. Size determines everything for a star. Its temperature, its color, its brightness, its lifespan, and the manner of its death. The sun, by stellar standards, is reassuringly average, Not too massive, not too small. Warm enough to sustain life, stable enough to sustain it for long enough. We are lucky, in the particular way that depends on there being someone to feel lucky. The stars in the night sky are not all the same. If you look carefully or look at photographs taken by telescope, you can see that they come in different colors. Blue-white stars are the hottest and most massive. Stars like Rigel in the constellation Orion burning at over 10,000 degrees on their surface, so hot that they emit most of their energy in ultraviolet light. White and yellow-white stars are the next step down. Our own sun falls into this category, a yellow dwarf, technically, though it appears white from space. Surface temperatures around 5,000 or 6,000 degrees. Orange stars are cooler and older, often evolved stars that have expanded from their original size. Red stars are the coolest of all. Both the small, dim red dwarfs at the bottom of the main sequence and the enormous red supergiants that represent the late stages of a massive star's life. Betelgeuse, the famous reddish star in the shoulder of Orion, is a red supergiant. So large that if it were placed where our Sun is, its outer surface would extend beyond the orbit of Jupiter. And this brings us to an important point about color and temperature. When we heat a piece of metal iron, say it first glows red as it warms, then orange, then yellow, then white, then, if you could heat it hot enough, blue-white. Stars follow the same principle. Their color tells you their surface temperature. Red is coolest, blue-white is hottest. The temperature, in turn, tells you a great deal about the star's mass and how long it has to live. Astronomers can read a star's entire biography from its color alone. Every star is in a race against itself. Fusion requires hydrogen. Hydrogen is the fuel. And hydrogen, however vast the supply at the beginning of a star's life, is finite. Over the course of billions of years or millions, for the massive stars, the hydrogen in the core is gradually used up, converted to helium, accumulating in the center of the star as fusion continues in a shell around it. Eventually, the core can no longer sustain fusion. The outward pressure drops. Gravity takes over. The core begins to collapse. And something strange and spectacular happens to the outer layers. As the core compresses and heats, it releases enormous amounts of energy into the surrounding gas. The outer layers of the star respond by expanding, swelling outward to sizes that dwarf their original dimensions. The star becomes a red giant. Our Sun, in about 5 billion years, will expand into a red giant. Its outer layers will swell to perhaps 100 times its current size. Mercury and Venus will be swallowed. Whether Earth will survive depends on calculations that are still being refined. But the oceans will certainly be boiled away long before the final expansion. Red giants are enormous, luminous, and unstable. They pulse and throb. They shed their outer layers into space, slowly, over thousands of years. For a star like our Sun, this is roughly the beginning of the end. When a star like our Sun reaches the end of its red giant phase, the end comes quietly. The outer layers of the star continue to expand and disperse, drifting outward into space in beautiful shells of glowing gas. These shells are called planetary nebulae, a misleading name, since they have nothing to do with planets. They were named by early astronomers who thought they resembled the round disks of the planets as seen through modest telescopes. Planetary nebulae are among the most beautiful objects in the universe. Perfect spheres and rings and butterfly shapes of glowing gas, lit from within by the hot remnant at their center. That remnant is what is left of the star's core after the outer layers have gone. It is called a white dwarf. A white dwarf is a remarkable object. It is roughly the mass of our Sun, compressed into a volume roughly the size of the Earth. It is extraordinarily dense. A teaspoon of white dwarf material would weigh about a ton on Earth. But it is no longer fusing. The fusion has stopped. There is no more fuel. A white dwarf is a cooling ember. It still glows intensely hot when newly formed, cooling gradually over billions of years. It will eventually cool to the point where it emits no visible light at all. At that point it becomes a black dwarf, the cold, dark, dead remnant of a star. In theory. In practice, the universe is not yet old enough for any white dwarf to have cooled completely. Every white dwarf that has ever formed is still glowing. The oldest ones are dim and red, cooling towards the end of their long evening. But none have reached darkness yet. The universe is still young. For stars with more than about 8 times the mass of our Sun, the end is not quiet. It is one of the most violent events the universe produces. When a massive star exhausts the hydrogen in its core, it does not simply expand into a red giant and gently shed its outer layers. It goes further. Its core, under the extreme pressure of gravity, becomes hot enough to fuse helium into carbon, then carbon into oxygen, oxygen into neon, neon into silicon, silicon into iron. Each fusion reaction releases less energy than the last. Each one buys the star a little more time. But the process accelerates. What took millions of years for hydrogen fusion takes only centuries or decades at later stages. And then comes iron. Iron is the end of the road for fusion. Up to iron, fusing atoms releases energy. The products are more stable than the ingredients. But iron is already the most stable configuration of matter that fusion can produce. Fusing iron requires energy rather than releasing it. When an iron core accumulates at the center of a massive star, fusion stops providing outward pressure. Gravity, now unchecked, causes the core to collapse in less than a second. A core that was the size of the Earth collapses to a sphere roughly 20 kilometers across in a fraction of a second. The density it reaches is extraordinary. The protons and electrons of atoms are squeezed together to form neutrons. The collapsed core becomes a neutron star. And the outer layers of the star, still falling inward in a great avalanche, slam into this newly formed, incredibly dense neutron star and bounce. The result is a shockwave of almost unimaginable power that blasts outward through the star's outer layers, destroying them completely, scattering them into space at a significant fraction of the speed of light. This is a supernova. A supernova is not just a violent ending. It is a creative act. Remember that fusion, the process that powered the star throughout its life, was building heavier elements. Hydrogen became helium. Helium became carbon. Carbon became oxygen, and so on up the chain. In the extraordinary conditions of a supernova explosion, the temperatures and pressures generated in those final moments, elements are forged that could not be made any other way. Gold, silver, platinum, uranium, the heaviest elements in the periodic table, created in the nuclear fire of a dying star and scattered across the galaxy in the explosion. Every atom of gold that has ever been mined, every gold ring ever worn, every golden object in every museum in the world, all of it was forged in the death of a massive star billions of years ago and scattered through space until it eventually ended up on Earth. The same is true of the iron in your blood, the calcium in your bones, the oxygen you are breathing right now. You are made of stardust. This is not metaphor. It is a literal description of your material composition. The atoms in your body were forged in stellar interiors over the previous generations of stars that lived and died before the solar system was born. They were scattered by stellar winds and supernova explosions. They drifted through space, gathered into the molecular cloud that eventually collapsed to form our sun. They settled into the disk of material around the young sun and accreted into planets. They became rock and then ocean, and then through the extraordinary process of life, they became cells and organisms, and eventually a conscious mind that can look up at the night sky and ask where it all came from. The astronomer Carl Sagan said it beautifully. We are a way for the cosmos to know itself. When the core of a massive star collapses in a supernova, it can become a neutron star. Neutron stars are perhaps the strangest objects in the universe that we know actually exist. They are typically about 20 kilometers in diameter, about the width of a large city, but they contain roughly 1.5 times the mass of our entire sun. The density is extraordinary. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. The gravitational pull at the surface is about 200 billion times that of Earth's gravity. Neutron stars spin very fast. When a star collapses from something millions of kilometers across to something 20 kilometers across, conservation of angular momentum causes it to spin faster. The same physics that makes an ice skater spin faster when they pull in their arms. Newly formed neutron stars can spin hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles. If the Earth is in the path of one of these beams, we detect a pulse of radio waves, with every rotation as regular and precise as the ticking of an astronomical clock. These pulsing neutron stars were called pulsars when they were first detected in 1967. The discovery was so regular, so precise, and so unlike any known natural phenomenon that the astronomers who found them briefly, and only half-jokingly, designated them LGM-1. Little green men. The universe is good at producing things that look, at first, like they shouldn't be natural. For the most massive stars, those with perhaps 20 or more times the mass of our sun, even a neutron star, is not the final resting state. The collapse does not stop at the neutron star. Gravity wins completely. The matter continues to compress. It passes through every known stable configuration of matter, and then it reaches a state that physics cannot fully describe: a singularity, a point of infinite density. And the region of space around this singularity, where gravity is so strong that not even light can escape, is what we call a black hole. The boundary of a black hole, the point of no return, inside which everything falls inward and nothing can escape, is called the event horizon. At the event horizon, the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing that crosses the event horizon can ever return. We cannot see black holes directly. They emit no light. But we can detect them by their effects on everything around them. Gas falling into a black hole forms an accretion disk, a swirling, superheated ring of material spiraling inward. As it falls, it heats to millions of degrees and emits X-rays in enormous quantities. These X-rays are detectable by space telescopes and have revealed black holes scattered throughout our galaxy. We can also observe the motion of stars near a black hole. Stars near the center of our galaxy, the Milky Way, have been tracked for decades, moving in tight orbits around something invisible at the galactic center. Their speed and orbital shape reveal the gravitational influence of an enormous mass in a very small volume. That object is called Sagittarius A*. It is a supermassive black hole, not the remnant of a single stellar collapse, but something far larger that formed through billions of years of mass accumulation. Its mass is approximately 4 million times that of our Sun. It sits at the center of our galaxy, quiet most of the time, occasionally flaring when something falls into it. All of this, billions of light years in every direction, rotating slowly around it. About 4.5 billion years ago, in an outer arm of the Milky Way, a molecular cloud was disturbed. Perhaps it was the shockwave from a nearby supernova, a ripple of energy from the death of a massive star passing through the quiet cloud like a wave through water. Regions of the cloud began to collapse. One of those regions collapsed into what would become our solar system. At the center, the protostar grew. Hydrogen fell inward. Temperatures rose. And about 50 million years after the collapse began, nuclear fusion ignited. Our Sun was born. The remaining material, the gas and dust that hadn't fallen into the protostar, settled into a flat, rotating disk. Over millions of years, tiny dust grains stuck together, forming pebbles, then rocks, then planetesimals, then the early planets. The young Sun blasted the inner solar system with radiation, driving away the lighter gases hydrogen and helium from the innermost planets and leaving behind rock and metal. The rocky planets formed: Mercury, Venus, Earth, Mars. Further out, where the Sun's radiation was weaker, the gases could accumulate. The gas giants formed: Jupiter, Saturn, Uranus, Neptune. And on the third rock from the Sun, a planet of blue oceans and grey continents, orbiting at exactly the right distance to maintain liquid water on its surface. Something extraordinary began to happen about 3.5 billion years ago. The atoms that had been forged in stellar interiors, scattered by supernova, gathered into a molecular cloud and collapsed into a solar system. Those atoms began to organize themselves into molecules, into chains, into self-replicating structures, into life. Our Sun is currently a little under halfway through its main sequence lifetime. It has been burning for about 4.5 billion years. It has roughly 5 billion more ahead of it. In that time, it will gradually brighten. The Sun today is about 30% brighter than it was when Earth was young. In a billion years or so, it will be bright enough that Earth's oceans will begin to evaporate in earnest, and the conditions for life as we know it will become increasingly difficult. Long before then, in human timescales, the Sun will be fine. Its variation over decades and centuries is small. We have, in stellar terms, enormous amounts of time. In about 5 billion years, the core hydrogen exhausted, the Sun will swell into a red giant. The inner planets will be engulfed or scorched. Then the outer layers will drift away as a planetary nebula, a beautiful expanding shell of glowing gas, lit by the hot white dwarf at its center. A white dwarf that was once our Sun. It will cool, slowly over billions of years, from white to yellow to orange to red to dark. And eventually, in the deep future of a universe much older than the one we inhabit, it will go dark entirely. A cold, dark cinder, drifting through the fading galaxy. But not nothing. Never nothing. Everything it made possible, every moment of warmth on a face turned towards it, every ocean it evaporated and rained back down, every photon it poured into every leaf that ever photosynthesized, all of that will have been real, will have mattered in whatever way the universe allows things to matter. Look up tonight. Or imagine looking up. Those points of light are not decorations. They are engines. Nuclear furnaces burning through timescales that make the whole of human history look like a single afternoon. Some of them are near the beginning of their lives. Some are near the end. Some that you can see tonight no longer exist. The light reaching your eyes left them thousands of years ago, and the star it came from may long since have faded or exploded. You are looking into the past every time you look at the sky, and you carry the evidence of that past inside you. In the iron of your blood, the calcium of your bones, the oxygen filling your lungs right now. Stars burned and died long before this planet existed, and the atoms they forged in their final moments became you. You are not separate from the universe. You are a part of it, briefly conscious, briefly wandering, made of the same material as everything you are looking at. That seems like a good thought to carry into sleep. Thank you for spending this time with IQriously. Rest well.